second morning session on quenching and compaction. First speaker is Avishai. He will talk about this magic scale of galaxy formation where everything happens. You have 20 minutes. Thank you so much.
Morning. I'd like to address a very basic issue in galaxy formation, namely, what is the origin of the magic scale of galaxy formation, 10 or 12 solar mass? I'll of course go back to very basic stuff, old stuff about supernova and hot CGM, which is the basic theory behind it, and allude to some new stuff about how this relates to compaction and black hole growth, also associated with the same scale. So I'm talking about this peak efficiency of galaxy formation around 10 or 12 solar masses of halo, where we have low mass quenching on smaller scales and high mass quenching on larger scale, giving us a lower stellar mass to halo mass compared to this peak of efficiency of galaxy formation. Also, black holes and AGN tend to appear mostly on the high mass end. This also relates to the famous Maddow-Dickinson diagram, where this is really to be blamed to low mass quenching. This is really to be blamed to high mass quenching plus the decrease of accretion rate at late times when the universe expands. And this is where typical halos, namely the press sector kind of halos at redshift 2 are at this magic scale. So this is not just a special time redshift 2 in the universe. It actually comes from a special mass, the same magic mass. So this is the typical mass in stars, in halo, or in virial velocity that I'm going to try to ask, where does it come from? Hot CGM, real shock kicked in very early work by these people, and our own work about shock instability say that the CGM in the halo becomes hot when the mass is above this critical mass. Supernova feedback, on the other hand, is known to be efficient only below a similar critical mass. And this was started with Larson and put forward by Joe Silk and myself many, many years ago. Now, I would try to argue that the compaction events to blue nuggets and the following quenching occur at this typical critical mass originating from these two physical phenomena. I will try to argue that the black hole is suppressed by supernova feedback on smaller mass scale when this is relevant, and then black hole growth is triggered by the compaction events. Finally, quenching is happening above this scale, partly because of the compaction, partly because of the hot CGM, and this will be what I'm going to tell you now. So this is the Dekel and Birnbaum work. The critical halo mass is where the real shock is stable and you have a hot CGM. What you have is gas going through the shock, hits to the real temperature, and then compression on dynamical time scale competing with the radiative cooling. And when the cooling is slow, you have a stable shock, which is at the mass scale we were talking about. Now, here's time, okay, and here's mass. And you all know about the typical halos, the pressure sector mass, which grows very fast. And this is the shock heating scale, a la Dekel and Birnbaum. It's pretty constant with time, and it hits the typical halos around redshift 2 or redshift 1. Very important coincidence. You have a hot CGM above this mass and a cold CGM below this mass. There's one fine-tuning here that at high redshift you can have cold streams within the hot halos, which add the mass scale actually goes up as an upper limit for galaxy formation. And indeed, simulations, first by Oakvirk et al. And Tessier, and then by ourselves, really confirm this behavior very nicely. Recently, Peter Baruzzi showed this diagram for the star-forming fraction in galaxies in the same diagram, and you can't fail to notice the behavior consistent with this very simplified theoretical prediction, that you are quenched about here, and you can make star-forming galaxies below there, including this whole strip. 2, supernova feedback. 3 was one scale, 10 to the 12th solar mass or a little below. Where did this come from? Dekel and Silk. The idea was that the energy the supernovae can really feed to the ISM has to do with the number of supernovae performing stars, the energy per supernova, the star formation rate, and the cooling time of the supernova remnant because it loses all its energy. Now, if you parameterize the star formation rate in the usual way, proportional to the stars that actually were formed, you end up with this becoming proportional to the stellar mass. And it turns out that what we found in Dekel and Silk, that these ratios of cooling time to free fall time is a constant when the cooling curve is in the range where it goes down like 1/T, where this is relevant to small galaxies. So what we have here is the supernova energy is the stellar mass times the constant, which is the typical velocity relevant to supernova feedback, around 100 or 120 kilometers per second. Now, to make the supernova energy effective, you want to compare it to the binding energy of the gas in the halo, which has this kind of energy. And if you equate those two, and you assume that you are at the peak efficiency of galaxy formation, such that all the gas that went into this halo during the history actually made stars, you compare those two and you get a typical velocity of 100, 120 kilometers per second, which correspond to our magic mass at redshift 0. The same magic mass, different physical process, different cooling or different scales, same mass. So if I take this diagram and add my supernova mass, a constant velocity in redshift looks like this. And as you can see, in the relevant range, redshift 2 or 1, it's pretty much the same scale. Somehow, supernova feedback and the heating of the CGM conspire to give you a very similar critical magic mass. I want just to give you a clue. Everybody asks, well, now everybody talks about this diagram. We can also predict from supernova feedback the slope here. You just compare those in the regime where the stellar mass is much smaller than the gas that came in, namely a lot of outflows. This comparison immediately gives you m star over m halo that goes like v squared or m to the 2/3. So it's going to give you a line very much in agreement with what we observe at different redshifts as universal slope of 2/3. If you are at the peak right here, where the stellar mass is like the total gas mass, which is proportional to the real mass, you end up with a constant explaining this turnover and then going down. Number 3 is the compaction event to blue nuggets, which me and others will talk about it here today. I'm going to use the Vela simulation by Daniel Severino, which we already produced here with very high resolution in zoom-in galaxies. And we see there the wet compaction gas that was diffused became compact because there was some merger or counter-rotating stream or some event that brought in gas right away. Compact gas core with high star, you can look at this as star formation rate. That's the blue nugget. And then the gas is depleted simply by star formation rate and by outflows due to star formation rate. And new gas comes in and give you this rotating ring, which Sharon after me will tell you more about this. In terms of the stars, you form this blue nugget that become a red nugget while keeping sigma 1, if you want, constant, the internal central density constant. So that's the blue nugget phenomena. In terms of time, the gas mass simply jumps by a factor of 10 within 1 kpc. and then depleted. So that's the compaction, that's the quenching, and this is the star formation rate just following the same thing. And this is what the stars are doing, and they become baryon dominated in the middle, as opposed to being dark matter dominated before or pre-compaction. What? Another little compaction. Maybe it's the one you're looking for. If you look at compactness here, thank you, and star formation rate here, or specific star formation rate here, you see this very universal L-shaped diagram in the orbits that you see here. Diffuse galaxies compactify to blue nuggets and then quench along a constant sigma 1 into red nuggets. This is the blue nugget phase and the L-shaped track. Of course, we observe this. If we put all the redshift beams together, shift sigma 1 a little bit, we see this L shape in the Barrow et al. Observed compaction and quenching. Along those lines, we see the blue nuggets right there. So the simulation really reproduced this very well. So we have these blue nuggets in gas and stars, and we say we have the red nugget with the new extended ring of gas in the later stage after gas depletion. The key that I wanted to point out today, I'm talking about the magic mass, remember, is that the compaction, the main compaction event, the big one that leads to quenching and to baryon dominance in the middle, occurs typically at the same magic mass. You see the halos above 10 to the 11, below 10 to the 12. Each point here is a different galaxy at the point of the blue nugget. Okay, at the peak of the compaction event. You can look at it also as stellar mass, but I think the real mass is the real physical scale we are talking about. So somehow, the supernova feedback scale and the CGM, hot CGM scale also tell the compaction when and where they can be very successful in, in making the blue nugget and then quench. Somehow those are the two mechanisms that do the same thing. I want to remind you, and Sano Takela is talked about this, we have this behavior of compaction bring you up to the top of the main sequence, quenching bring you down, but you may go up again and only eventually, once you're above the critical mass, properly quench. So we try to understand this by comparing the inflow, the accretion rate, and the depletion time. That has to do with consumption of star formation as well as outflows. And here, if the inflow rate is faster than depletion time, you will compactify properly. This is in a paper by myself and Andy Burkert. Then you go up here, and you are bounced back because the depletion time becomes more efficient than the inflow. Star formation is high because of the high density in the middle. However, the inflow is low because the gas has shrunk. There's no gas to immediately flow in. So you try to quench. However, if you're not massive enough, gas continues to come in through the halo. And if the accretion rate is high because you're at high redshift, you'll have the inflow winning again against the depletion. You have a replenishment, and you will bounce back up and then back down. But now, because you are massive enough, and there's no gas supply by the hot CGM, plus AGN feedback is turned on, as I'll tell you in a second, plus the accretion rate is not so high anymore because you're at low redshift, you can really quench all the way down to the red sequence. Here are two galaxies. You see the bouncing up and down because of the interplay between inflow and depletion, and eventually, when you're at the right mass, critical mass, you quench down. If you look at this inflow rate over depletion rate here, and you compare it to the rate of motion upwards or downwards across the main sequence, you see, again, each galaxy is here, that here you move up and you have wet compaction because the inflow is stronger than depletion. But here, where the inflow is weaker than depletion, you are moving down and you have a quenching attempt. In a diagram, the same diagram we showed before, you see how this ratio changes below and above unity, and explain to you why you have full quenching here and only quenching attempts there. So the quenching mechanism is, as I told you, interplay between those two games, and long-term quenching is achieved when you have a hot halo mass above the critical mass. Also useful to have this when the accretion rate is low, at low redshift, and plus AGN feedback. So let me go to my last point about how all this relates to the black hole growth in our galaxies. A famous old diagram indicating that AGNs really appear among the emission lines only when you are at high mass, above our magic mass. Only there AGN seems to dominate the emission line. Where did this come from? Why do we talk about AGN feedback as the mechanism of quenching only in massive galaxies? Well, I don't know anything about black hole physics that give you this scale. Maybe Richard knows, he is the one who thought about it maybe as long as I do. I don't know of anything in the black hole that tell you the magic scale. I think it's a secondary effect that has to do with the other two mechanisms I talked about. Here's a beautiful simulation by Dubois et al. I think, Melanie, you're on this paper, right? You're not. Neighboring paper. You inspired this paper by being nearby. Anyway, this is by the Paris people, IP. What they did is simulations, once with supernova feedback, the other one without and with supernova feedback. And this is the black hole growth in time. What you see is that if you have no supernova feedback, there's a rapid growth of black hole from the very beginning of the simulation. But if you have supernova feedback, the black hole growth is suppressed until, in this case, redshift 3.5, and then suddenly there's a rapid growth. Here there was a merger, a 1 to 4 minor merger that triggered this compaction. This is a compaction event. As you can see, the effective radius drops, and the mass scale is 10 to the 10 solar mass, exactly where we expect the compaction to occur. Now, the idea is that, again, below this mass, supernova feedback suppresses the black hole growth. The compaction here overcomes the supernova effect, and it just happens when supernova are not important anymore, because you reach the magic scale. Then you have the rapid black holes, and then you trigger the AGN feedback right at this mass scale, which can help you quench. Two more simulations from the horizon, New Horizon, analyzed by Sharon Lapiner and Johan Dubois and me. As a function of time, what you see here, gas compaction event followed by black hole growth event. Gas compaction event followed by black hole growth event. The same thing. And I told you about Richard. This is from the Eagle simulation, and you see the same thing. Okay, happening very robustly in the same mass scale, halo mass scale of 10 to the 11.7. So the idea is, again, that we have a supernova phase below the critical mass with black hole growth suppressed, and also blue nugget formation suppressed and weakened because of the same supernova effect. Then you have the trigger activating the black hole growth at the critical mass, which is the compaction event, now overcoming the supernova feedback at the magic scale, the supernova stops being important. And finally, post-compaction, we're at the hot CGM phase, which allows the black hole growth. The supernova winds become bound for two reasons. The halo potential keeps them in, and the hot gas keeps them in, something that again in Richard paper is well explained by avoiding buoyancy of the cold supernovae in the hot CGM. So the gas falls back in, supernovae are not important anymore, and then the AGN self-regulates with the accretion, and the AGN help you keep the CGM hot and suppresses star formation rate. Dekel shows this in the observational plane of compactness versus star formation rate. The color tells you the fraction of host galaxies with X-ray AGNs, and you see very nicely agreement with this scenario where there's high fraction of AGN in the blue nugget phase as predicted by this very simple theory. Consistent with the idea that it's the compaction that triggers the AGN, which then helps the quenching, which is primarily triggered by the compaction inside, by the hot CGM preventing gas supply, and then the AGN really help you further keeping the CGM hot. So I was blaming everything on these two physical processes, and I was trying to allude to these details that these two physical scales help you contribute and really see a major transition in everything in galaxy properties below and above the magic scale. So I leave you with this picture. Thank you.
Thank you, Avishai. Questions for him? Yep.
So what would the universe look like without black holes? If they're just helping, are they going to make so much difference?
Our simulations so far, the ones that Sharon is going to talk about, did not have black hole. And you see everything except that the quenching is not full. So the quenching is starting at the magic scale, but you don't really complete it and you don't preserve it for a very long time. So AGN to me is a helper for quenching at high masses. Besides, without black holes, it would be very boring, wouldn't it?
Well, it's nice, you know, that I would argue that the outcome of the universe depends on this, you know, singularity in Einstein's gravitational physics. That's kind of cool. Are you going to argue that? Yeah, try anyway. I might not get quite that far. But...
What about the nature of the dark matter particle determining the cosmology?
Well,
even a smaller scale.
Okay, another quick question. I have a quick one, because one thing you mentioned is that in the simulation, the blue nugget builds an envelope around. The blue nugget builds an envelope around, a diffuse envelope around.
A ring, yeah, the external ring. It's a disk.
It's a disk of stars, I guess.
Of gas making stars.
And I'm not sure we see that in the observations, actually. So
okay, many observers tell me that if you look carefully, you see this.
Okay.
And we can discuss this.
Okay.
It's not easy because it's a low surface brightness, low surface density thing.
Okay. Last one, and then.
I don't know if bars really form at high redshift because the system is so gaseous. Bars is a typical phenomenon of low redshift, and maybe there they have a role in predicting black holes.
Okay. Let's thank Avishai again.
Thank you.